Hi everyone, I'm Dr. Prakash Chaki from NEC Laboratories in Japan, and welcome to this conversation. Today we'll be exploring channel coding 6G and much more with Professor Muriel Médard from the Electrical Engineering and Computer Science Department of MIT. Professor Médard holds 3 bachelor's degrees, her master's degree and PhD, all from MIT. She is the NEC Professor of Software Science and Engineering in MIT's ECS department, where she leads the Network Coding and Reliable Communications group. She's also a co-founder of Optimum. Muriel is a member of the US National Academy of Engineering, the German National Academy of Sciences, a fellow of the US National Academy of Inventors, and much more. She holds honorary doctorates from the Technical University of Munich and Aalborg University. She has earned numerous accolades, including the 2022 IEEE Kobayashi Computers and Communications Award, the 2018 ACMC Comtest of Time Award. She has served as the editor-in-chief of both IEEE Transactions on Information Theory and IEEE Journal on Selected Areas in Communications. And she was also the president of IEEE Information Theory Society in 2012. With that, we'll start this conversation, setting the stage with a little broad and central question. Muriel, what is 6G for you? Or rather, what is your wish list for 6G?
That's a really good question. I think you can ask 10 people and get 20 different answers, because some people have more than one opinion. Um, my hope for 6G is that it's the first standard that allows what I call the APIization or modularization of the different parts of a system. And if you look in general in networking and software more broadly, the way things work together is that there's an API. It's not that you have a monolithic standard that dictates everything. It just dictates what things need to do, what modules need to do, and how they fit together with each other. Um, and in that way, the standards coming out of 3GPP are very odd. I mean, you could even say to some extent it looks almost um, antique to have a very prescriptive recipe for everything that goes, MAC, PHY, high barrier Q, that all of these things are so massively constrained, rather than being more defined as units. Some of them that can be more plug and play, some of them could even just be not turned on, and instead defining the APIs. So I'm really hoping that 6G moves away from that very prescriptive monolithic approach to something which is, let's say, a more modern approach to system design, such as, it's basically the case in other areas of software and definitely other areas of networking.
That's very insightful take on how the progress has been on 6G and 3GPP. Okay, just following up on that, 6G's standardization at 3GPP has kickstarted last month. And one news that has been doing the rounds a lot is about cyclic prefix-based OFDM coming back. One thing that closely follows modulation is coding.
Mhm.
So coming to coding, how do you think 6G's coding might look like? How do you think channel coding stands today, and what are the most urgent open challenges remaining?
Yeah, so I think that coding today falls still within this framework of being highly constrained. Um, and I would argue not for a particularly good reason. Let's actually go back a little bit because that helps looking forward. So let's go back to 5G, which is nice and fresh in everybody's minds. You have this kind of strange cohabitation between CRC-aided polar codes for the control channel and low density parity check codes for, which actually, were my predecessors coding thesis at MIT. I mean, we're talking 1962, Bob Gallagher, that was his doctoral thesis at MIT. He was actually my doctoral advisor. Uh, and then you have CRC-aided Polo codes, which are much more modern. We're talking 2009 for Polo codes, and then the CRC-aided aspect came, say, in the 2010s and so on. And they don't look anything like each other. They really, really don't, right? So you have these two completely different modules. And the reason for that, bluntly, is just that it was a compromise for reasons that are at least partially not technical. Let's put it that way. Um, if you go back to 4G, you had actually effectively convolutional codes and then turbo codes, which were built on this convolutional code. So at least you had something which was a little bit more modular, in that you had a module which was a convolutional code, and either you took it by itself or you took it as part of a turbo code. And basically, you were building the longer codes from something that looked like the shorter codes. You go to 5G, the long codes, LDPCs, are built from, teeny tiny codes, basically like, CRCs effectively, like 1-bit CRCs, you know, stuck together, and they don't look anything like a Polar code, nothing like it, right? So, and so you go, how is this coming about? What's the rationale? My hope for 6G, and this gets a little bit into Grand, for instance, some of the work that the co-inventor of Grand, Ken Duffy, who's now chair of the math department at Northeastern University. He was head of the Hamilton Institute in Ireland when we started this work. What he and I have been doing is around looking for a universal decoder for basically not necessarily short, but sort of low to moderate redundancy codes, where redundancy is literally just, the bits that are there to do the correction. And then in order to build long codes, take those shorter codes and build actually very classical types of constructions, literally just product codes, like good old-fashioned 1950s product codes. Fun fact, product codes came from Elias, who was Bob Gallagher's thesis advisor at MIT. So there's a line there.
Okay, this is the whole generation.
There's a whole generation. So it's basically like going to like my academic grandfather's codes, you know. Um, and they're great codes and they're capacity achieving. Another thing that always puzzles me is when people say, "Oh, but LDPCs are capacity achieving." Any random code is capacity achieving. We've known that, since basically the 40s, and with basically with Shannon, and then the 1960s, 70s, Gallagher shows that any random linear code is capacity achieving. So like, anything's capacity achieving. I go into my sock drawer, pull something out, it's capacity achieving. How is this? How is this a wondrous thing? The only thing is that then you have to decode the code. So, you can use product codes. And, Ken and I have shown in many cases you can, get a performance that is at least as good and it may sometimes better than 5G LDPCs, right? And this is without having the sort of massive investment or industrial research that has gone into this. Is just, academic, Mad Lab and a cup of coffee type thing. So I think that we're really missing a lot of opportunity right now to have a much more flexible system. Now, you could say, well, why do I care if it's flexible or not? Well, we care because Otherwise, we have very few choices and we're really constrained, right? What you'd like to do is to say, look, here are my needs. Um, this is my latency budget. Um, this is what my block error rate should be. Um, you know, go and construct me the best code, for whatever rate, it's like I have this latency, I have this block error rate, I have this SNO. Just give me the best thing right now. And if you only have, you know, a small roster of codes to pick from, that's not going to happen. So having modularity is not just about, if you will, intellectual hygiene. It's also about having flexibility. We talk a lot about what's the role of machine learning and AI. Machine learning is, and certainly the way, we teach at MIT, when particularly even starting at the undergraduate level, is about optimization, right? So you have a really complicated optimization problem, and if you could solve it with pen and paper, you'd be done, but it doesn't lend itself to that, so you do other things. What's the point of putting really sophisticated optimization algorithms when your space over which you're going to optimize is tiny? You know, like if I ask you to choose between only two possibilities, you're probably not going to run a machine learning algorithm. You don't have a lot to pick from. It's pretty obvious which one's best, right? So if we really want, to do something which is much more powerful and much more adaptive, we need to have that modularity and that adaptivity all through. You can't say, okay, I'm doing machine learning, but you know what? I actually don't have a lot of choices to pick from. Well, you can, but it's not intellectually aligned.
Well, there are quite a few things that's coming to my mind right now. Uh, so you spoke about machine learning, and talking about that with the recent buzz around generative AI, do you see that playing a role in optimizing or improving the coding schemes for communication systems in future?
It's a really good question. The thing there is that we already know, this goes back to the capacity. We already know how to get pretty darn close to capacity. And you're not going to do better than that. Uh,
Absolutely.
uh, and the reasons we're not doing it now, when we're not doing it, is again because of this really top-down approach that standards have taken. And I think it's an antiquated approach. I think it needs to evolve.
Yeah. So yes, as you rightly pointed out, achieving the capacity is probably no longer the goal for coding theorists, but achieving the capacity or approaching the capacity in finite length, shorter
Mhm.
length codes, that probably still something that keeps teasing the coding theorists.
So
Don't you think
that's
so?
that's a great point. We've done some work with Ken and actually recently also with our student Alex Mariona, and there are upper and lower bounds at finite lengths, right? And we plotted what happens with a random code decoded by Grant at those lower, shorter lengths. And basically, it was right between the best achievability bound and the converse.
Mm.
It was right there. For the kinds of bit error rates that we usually look at, which are like, 10 to minus 2, 10 to minus 3. So and if you look at what are generally considered to be short length approaches like the Polyansky et al., those for very, very high bit flip probabilities, like 20%, which is not what we see in commercial systems ever, work. But if you go to actually 10 to the minus 3, 10 to the minus 2, raw bit error rate, which is more representative, those actually are often actually above the converse. So they're not tight at all. So it actually, those shorter code lengths for, you know, reasonable n minus k redundancy, we know how to do it. Just recently had a paper on that at Allerton, the Allerton conference just last year with Alex and Ken.
The standard people, for some reasons, they have an inclination of introducing some new code in every generation of communication systems. So, for example, if we look at the previous generations, uh, block and convolutional codes were signature technologies in 2G and 3G, then Turbo and LDPC in 3G and 4G, and then, as you just mentioned briefly before, polar codes and LDPC coming into 5G. Is the next frontier in inventing new codes or finding better ways to decoding existing ones?
That's a really good question, and I think Prakash, you hit the main issue. We talk a lot about coding theory, but again, remember, a random code would do. So it's really about decoding. The reason we make these funky codes is because you need to decode them, not because necessarily of the code's inherent qualities, if that makes sense. And of course, there's a little bit of both, always. But the biggest thing is around decoding. Again, let's go back to product codes. The codes are perfectly good. The reason they weren't being used is like if you look at, say, the original turbo code, and by that I mean like the Pindia iterative decoding, not the turbo codes that later became best known, which are two convolutional codes with an interleaver in between, etc. And usually a whole lot of puncturing. That's that's a separate matter. But if you look at the original turbo codes, you can take the same codes and do much, much better than with Pindia if you use Grand. And even if you don't use Grand as the component decoder, say that those components were, say, a CA polar code, and you want to decode it with a, you know, CRC-aided successive cancellation list decoder, because that's what you already had lying around. But using Grand to estimate the soft output, then actually you get massive gains versus Pindia. So the code, and this gets back to the code decoding, the code was fine. There was no problem with the code. It's just that the decoder wasn't fully availing of the code, right? And, same thing if you look at, generalized LDPCs, like the stuff that Landmeyer and others have done, which is basically, very, very coarsely. It's like a product code, except rather than having, rows and columns, you have sort of rows and diagonals. Okay. Again, that was very difficult to decode, but you can use soft input Grand with soft output iteratively, and you can get very, very good results. So I think that it's really important to remember the decoding. I know we talk about coding theory, and I understand, and I'm perfectly guilty about talking about coding theory, but to a large extent, it's more about the decoding is what has been causing the choice of codes, if that makes sense. And so, they were perfectly good codes that were not used because people didn't know how to decode them, or they were perfectly good codes that were being not used because the existing decoders massively underperform relative to what the code could actually do.
Just to add some personal anecdotes to this whole discussion on polar codes and LDPC, how they came into 5G. So I was serving as a 3GP delegate, RAN 1 delegate at that time.
Oh,
And
bless you.
that was back in 20, back in 2017. And people were really debating about just a few fractional dBs of difference between different codes, and then polar codes entering the picture. And then the whole discussion shifted to CRC-interleaved polar codes, like distributing the CRC bits
Yeah.
across the frame, and then trying to do early termination when there is a decoding error. And that discussion itself, it extended for several months before people came to the conclusion. Yeah, so there are many, many funny stories there.
Oh, Prakash, so it should be you that we're interviewing about this, not me. Here I am saying, well, let's say that everything was not technical. You would know way, way, way better than me.
Uh, in one of your recent papers that you have submitted to IEEE CTN, uh, a new coding and decoding for 6G, you describe 5G's architecture as layered with legacy technologies. uh, why has this layering become such a bottleneck, and how could modularization that you just spoke about earlier, this modularization in 6G, how it can accelerate progress? Could you please shed some more light on that?
Yeah, thanks for bringing that up. So, in that article, just to level set, particularly for our listeners here, I propose a rough modularization, which I think follows basically what we're doing already. It just as engineers, this is kind of what we're already doing. Maybe we're not taxonom giving that taxonomy, but one is more around the transport part that deals basically with erasures, right? And erasures happen because there were errors that didn't get corrected, because there were losses from whatever, right? So it's basically the erasure management. The next block is the error correction, what we were just talking about. Uh, and so if the error correction doesn't work, that then it goes to the erasure correction. The block after that is basically everything to do with the medium access, and in particular the multiple access. We were just talking actually about, the OFDMA and things like that. Um, and then you have the actual modulation, right? And then, of course, on the other side, you have the demodulation, also the multiple access, the decoding, and the correction of the erasures. Um, and right now, this is all completely munched. And I really think they should be separated, and that these units should just have APIs between them. So that, if you tomorrow, Prakash, come up with a, fantastic coding, decoding scheme for erasure correction, great, you just stick it in that module. That's it. As long as what comes in is what's expected from the erasure correction the erasure management module, and as long as what goes out is, compatible with the medium access module, then, who cares what you do in between? Literally, like, who cares? It should be irrelevant, right? All of these modules should just be flexible, and this will also enable innovation and enable a real marketplace with competition, right? We're not seeing competition right now, I would say. Certainly not that much competition of ideas. And I think for an industry that is very risky.
Okay. So in your proposal, I read that you compare the reduction in retransmission achieved by network coding as compared to conventional ARQ and HARQ.
Yeah,
Is that right?
that's right. So that's one example, right? That's one example. But if you think of just the whole problem as being a problem of managing errors that were not, corrected, if you think of that more broadly, then there are many things that people can do. You can do the hybrid ARQ, you can do ARQ, you can do hybrid ARQ with ARQ, the way it's been done right now in 5G, was already done in 4G. There's a lot of different things that you can do. Okay. Um, and why should it be prescriptive? Right? Or you can code and use network coding and not have to deal with it with retransmissions, or deal with it with retransmissions where you code for most of the erasures to be corrected, and only every so often do you retransmit if the forward erasure correction wasn't enough, right? I mean, the world's your oyster. Why are we picking a single system? It's really, really complicated. And there's no reason for it. There's really no reason. I mean, if you look at the hybrid ARQ system currently in 5G, it is extremely inflexible, right? Um, and actually, with collaborators at JMA and my former postdoc, Vipinda Vasudevan, and my student Laura Landon, we were trying to even do this, say, in Oron, where we were trying to improve. And it was so hard to even get the software to work that in the end, it was easier to work directly on the hardware.
Mm.
And that was much harder than similar work we had done on the previous generation, right? Um, so it shouldn't be this hard. We shouldn't have to go and spend months of not very productive work and, getting me very close to using unladylike language in front of my in front of my students for something that should just have been modularized, right? Uh, Otherwise, you basically just, in order to do any sort of improvement, engineers to be able to innovate are basically forced to hack into stuff. Um, Occasionally, okay, it's kind of fun, but it's not a way to run a system. That's not, that's not what grown-ups do.
I see you also speak about security. How does coding itself serve as a security tool in such heterogeneous networks?
That's a really good question. Um, Let me do a little bit of an aside, which is going to seem a little bit removed, and then we come back.
Yes, sure.
Because it will actually set the stage a little bit. So uh, I'll ask for your indulgence for a few minutes. So um, there's a lot of discussion right now about quantum safe, right? What's going to
Mm.
be post-quantum security and so on. And different people and reasonable, knowledgeable people can disagree entirely onto when quantum computers will be here or not, right? Let's not even go in that direction. Again, 10 people, 20 opinions, right? Um, it's certainly the case that there's already, documented, and this has been in the public press, documented cases of entities already gathering information with the hopes of decrypting it later um, because of the expectation. Whether that expectation is right or not is not for us to decide tonight. But the expectation that quantum computing will become possible and enable the decryption of those vast troves of data, or at least some portion of it. Okay, so enter now what quantum safe encryption is. So, in the most caricatural of terms, traditional encryption tends to be about having functions which are difficult to invert. Okay. But if I give you a key, then it's easier to invert, basically. Um, and if you look at a workhorse of encryption like RSA that was co-invented by my colleague Ron Rivest at MIT, that kind of encryption was then by another colleague at MIT, Peter Shor, shown to be, at least in principle, fragile, let's say, in the context of quantum computing. That some of the things that would be difficult with a deterministic computer might be polynomial time potentially with a non-deterministic computer, basically, just very high level. And I'm waving my hands, but roughly this is representative. Okay, so let me get back now to the point. So what is post-quantum encryption? Well, if you look at the post-quantum encryption methods, they're actually all coding methods. The granddaddy of them all is the McLeish crypto system, named after the great late Bob McLeish, who was a faculty at Caltech. And, it has stood this test of time. Not many have, by the way. You see many of them being proposed and being broken the following year, 10 years later. It's definitely a tough area. But inherently, they're coding schemes. And they're not just coding schemes, they're error correcting schemes.
Mm.
Okay. So now you have a system where, and this gets back to this issue of having modularity. Now you have a system where it would be absolutely desirable for security to have your security also allow different kinds of codes. The
Mm.
coding flexibility is not just to get efficiency so that you're not stuck with just, the sort of really unexciting menus that we've had for a few block error rate curves in 5G. I mean, not that it didn't take a huge amount of engineering prowess to get there, but eventually you're like, okay, here it is, pick your poison. You just have a few curves and you pick one, right? But now this means that it's actually something that can enable your encryption, right? So having that flexibility is extremely, extremely desirable from the point of view of real security. I'll give you not something that I'm suggesting people do, but I'll give you a little vignette of
Mm.
where the two come together. So together with Ken Duffy, whom I mentioned, my former postdoc Rafael de Oliveira, who's now a professor at math in Clemson, my former postdoc Alejandro Cohen, who's now professor in EC at Technion, and my former student Zhang Chanhuo. So what we did is we took AES, right? Encryption, not an error correction code, right? We just took some bits, padded them, not even encoded them, just padded them, then encrypted them, and using GRAND, because GRAND is universal, use that to decode. So we're basically using the encryption for error correction coding. Now remember, I told you anything you find in your sock drawer pretty much is going to be close to capacity achieving. That includes encryption.
Mm.
And it did, I mean, not quite as well, but it did almost as well as a C Apollo code when decoded correctly. Actually, when decoded with the current state of the art, which is very suboptimal, the list decoding, it did better, right? So, the list decoding that's out there, this CRC-aided list decoding is very suboptimal, relative to GRAND. But, again, I'm not suggesting people run off and, use AES for error correction coding. It's a bit like, when people report that they managed to make a pickle Lay's, nobody's suggesting that you go and replace your yags with pickles. But, the point is, wow, that's pretty cool, right? That is pretty cool.
The general encoding and decoding units, or grand and orb grand chips, you suggest uh, they can replace multiple decoders with one universal decoder. Is this understanding right?
That is
So
correct. That is correct. Where for
how
longer codes, you basically use iterative decoding.
so how do you see this impact the hardware footprint and adaptability in general in 6G? This whole thing of replacing multiple decoders with one universal decoder, how is this going to impact hardware footprint?
Um, it should impact it positively, right? It should reduce the the
Right. Yeah.
hardware footprint.
Mm.
Um, you know, Again, that's one of the things modularity does. Rather than having to have, multiple different approaches, you just have the approach that makes sense for you, and you don't have to drag around, you know, oh, the all of the entire kitchen. Um, so that's, to me, it's just, and I don't mean to oversimplify, of course, in this conversation, there's always a lot of engineering to be done, a lot of things to explore, but just, you know, the chips have been shown to be extremely fast, extremely energy efficient. Um, Generally, from that perspective, more, have better performance than the chips that are dedicated to a single decoding, so, non-universal, right? Um, so, and we've done a lot of work on that with Ken, but also with our colleague and collaborator, Rabia Zizigil, who's a professor at BU. So, I mean, I think it's definitely something that should be considered. Let me put it this way. It's something that not considering it makes no sense.
Yeah. So
I mean, just
absolutely. Yeah. So with soft output grand, we speak about this time and again that simple product codes can outperform 5G LDPC codes, probably, right? Uh,
so that's what we've been researching. So far we see that, and again, it's if you, in particular, when you look at limiting the number of iterations, right? And I think this is something that's important to highlight. And of course, Prakash, you know this better than me, but you know, when you go to hardware, there's the stuff that's parallelizable and the stuff that's not parallelizable. And they don't fall in the same bucket at all, right? Because the stuff that's parallelizable, you parallelize and it goes super fast. And the stuff that's not parallelizable, that has to be serial, that's where your bottleneck is, right? It's actually basically it's Amdahl's law, right? It is actually Amdahl said, the slowness will come from the part that is not parallelizable. Okay, so it's Amdahl's law in coding, or in decoding rather. So if you think of something like a belief propagation system, say for an LDPC, so you have a lot of parallelization each iteration, but then you have a lot of iterations back and forth. And you have to stop at some point. Same with a, turbo code, right? You iterate. If you look with, the types of things we've been looking at, different kinds of product codes. And by the way, the component codes, They can be a CASC, a CA polar, they can be a CRC. Actually, funny enough, we found CRCs used as error correcting codes are often really good. Just going through Coopman's CRC
Mm.
list has been a trove of excellent codes, which were not being used as error correcting codes before because people didn't have grant, but now you can. So that's definitely a very fun place to go spelunk for good codes. We were talking about where to go look for good codes. Coopman's CRCs is a great place we have found. Um, and um, we see that there's all kinds of ways where you can, and with an amount of engineering, because remember, it's just Ken and me and a couple students, right? I mean, when you consider the level of effort relative to the level of effort that's been put in everything else, where you have, hordes of engineers, it's like, you know, this is a small little cottage industry on the
Mm.
side, right? Because we're all doing other things.
Yeah. Muriel, we have been talking about Grand for a while, but just for listeners who are new to it, just zooming back to Grand, why is gauging the noise so powerful?
Yeah. Uh, so the reason it's so powerful is because it's actually what you were trying to manage, right? So you're really looking at the problem, I would argue, in the correct way.
Mm.
You were decoding because the noise has had an effect. So if your point was to remove the effect of the noise, why are you looking at the structure of the code?
Mm.
The noise is your problem, right? You were
Mm.
doing things with the code to manage the noise, but the noise is the so you know. Here's an example. So we tend to think of correlation in the noise as being a pain, right? What do? We interleave, and then we make the noise look basically like white noise, right? That's what we do. If you come at this like an information theorist, you go, wait a minute. White noise is the worst kind of noise. It's the highest entropy noise. It's the one that's going to give me the lowest capacity. You took noise that has correlation, ergo lower entropy,
Mm.
and you made it by adding, by the way, energy, delay, you know, extra hardware, since we're talking about hardware, to make it
Mm.
look like the worst case noise. What are you doing? Like, what? It's the most bizarre thing on earth, right? You took something you took something where you're having higher capacity, and because you decided to pick an old-fashioned decoder and you didn't know how to manage the correlation, you turned it into the worst case. So you're taking everything you see and you're turning it into the worst case system because you built a decoder for a worst case. How is this a good idea? Well, it's not, right? It obviously isn't. Um, so, if you can take into account, and it's one, so if you look at or Grand AI, for instance, which is work that we did with the Ken and I did with Moritz Grunde, visiting student from Wolfgang Ucich's group in Technical University of Munich. You actually show that you can do much, much better. And it basically, you don't have to interleave to interleave. Your throughput is higher. Your latency is lower. You decode faster. Your rate is higher. I mean, everything, but that's an example, right? And But what are you going to do? Go into coding theory and build a different code for each and every correlation level of noise? No, right? The codes were all the same in this system that I just mentioned. They were all the same because you're only using the code mostly. You're mostly using the code just as a hash, just as a check to verify whether the noise effect that you guessed was correct or not. So when I teach this, so I used to, of course, teach coding the old-fashioned way. We've all gone through it. It was painful, right? Now I teach using Grant. Graduate course, I like to do in-class labs. You know, people MATLAB, by the end of an hour and a half, they have a working decoder that works across multiple codes.
Okay, that's
Okay?
cool.
In an hour and a half, just in-class lab,
Mm.
you know. And then I tell them, I say, okay, this is how I taught it to you. I taught it, and then I start teaching it. I tell, well, just so you know, because you're going to go out there in the working world and you're going to see this, the students are completely confused. Like, why are you doing that? Like, I don't know.
So probably this new generation of students who have like started looking at coding from Grant's perspective, they won't probably be able to relate to what was happening prior to that. Like, why were people looking at decoding like that?
It's really strange, right? So I go, well, and then finally I'm like, look, I'm not trying to justify it, okay? Just like, but, and again, I'm being a little oversimplistic, but not too much, right? Because the students immediately understand. They go, okay, you have a probabilistic description of the noise effect. You guess the noise effects from more likely to least likely, right? Most systems, most of the time, there's no error, right? That's your base case, but you need to check, right? And the code is a hash. The code is a hash. You subtract the effect of the error that you've guessed, and you hash and you go, is this correct or not?
It's not just the theoretical proposals on Grant, but I see that you have been actively involved in the chip designs as well for Grant.
Correct.
So, what has this whole experience of building Grand chip taught you personally about energy efficiency, latency, or flexibility?
It's a really great question. One of the topics I mentioned already, it's like it's when you talk about complexity, you have to really separate. It's about the time complexity, and you really have to separate the things that are parallelizable from the things that are not, right?
Hmm.
Anything that can be parallelized, anything that can be pipelined is completely different from something that has to happen consecutively, like iterations. Okay. So it certainly has taught me that. It's been a fantastic experience. I mean, it's not that I had never participated in doing chip design, along with actually uh, our current provost, Anantha Chandrakhasan at MIT, and we co-advised a student, Georgia Angelopoulos. We had made a chip for decoding and randomly network coding, so very low energy chip. It actually won an Globecom award. So I had been involved in that before, but never to the level that I have with Grant. Um, it's been a wonderful experience. I mean, a lot of it is, of course, working with Ken, working with Rabia, whom I mentioned before, and their teams, Arslan Riaz and, so many wonderful people. Um, but it's really also that, you have to look at things algorithmically. You have to look at things algorithmically. Um, let's look at OrbGrand, which is a way of managing soft input. There what you have is a problem that a priori looks really, really hairy, which is how to take into account the soft information in the guessing order. And through a variety of means that I'm not going to go into. And actually, Ken and I are writing a monograph currently on Grant, so um, we hope to release it soon, and we hope that maybe some of the people listening to the podcast will be interested. But you end up with a problem, which is a combinatorial problem, which happens to be an integer partition problem. And integer partition problems happen to be very compactly solvable from an algorithmic perspective. So I think that the algorithm side is really important. One of the very fortunate things I've had is um, at MIT, a lot of my teaching has actually been on the computer science side. Whether it's like math or computer science, which our students have nicknamed proofs, and more proofs, or whether it's our, introduction to algorithms for computer scientists. I love teaching those classes because, A, yeah, keeps me sharp in those domains. But B, it's so important to what we do. So I think the algorithmic side is super, super important. I don't know if I
Let's
answered
talk.
your question, but yeah,
No, you did.
yeah,
Let's
yeah.
let's talk a little bit about your new book, Network Coding for Engineers. So what is the current status of the book? It is completed. It
It
is
is
in the proofreading
completed.
stage.
It's completed, and I will send you your own copy, Prakash.
Thank you so much.
Absolutely. After
I'm
this, you have to
honored.
send me your mailing. Yeah, it's completed. It
That's
has
great.
appeared at Tripoli Press.
Hmm.
It has been co-authored with Ken Duffy, whom I mentioned, Vipinda Vasudevan, whom I've also mentioned, and another collaborator, Morten Peterson, who is the CTO at Nanoping, formerly Steinwolf. And it
Like,
requires, sorry, go ahead, go ahead. So get
yeah,
so
like
excited.
absolutely understandable. Like people who know you, they know about your extensive background in network coding. So like reading network coding right from your book, it'll be a fantastic experience for anyone who is interested in this subject.
Thank you,
Uh,
thank you. Yeah, we're very
what
excited
was
about it.
what
It
was your
was,
goal
yeah.
in writing this book?
The book was really, as the title indicates, to have engineers who don't need to have any background in finite mathematics,
Hmm.
basically with maybe a very standard background, undergraduate background in probability. Maybe they took like one probability of stats class, be able to approach network coding.
That's
Um,
amazing.
right. And so as a result, we also have a lot of Python code there. And we
Oh,
start from scratch. We start from scratch. We start that you don't know anything about finite fields. You don't know any number theory.
no prerequisites.
No prerequisites. We'll teach you all the number theory that you need to know to do this. We'll show how this applies to protocols such as TCP, et cetera, et cetera. So we assume that people know nothing. And if you don't program, that's also fine. You can just skip the parts that show sample code. Um, so it's really meant either for people to do an undergraduate course or a graduate course or a self-taught progress through the book. And in our introduction, we propose different combinations of chapters for different purposes of say a quarter, some universities in the US work on semesters, some work on quarters. So something for people who are teaching a 1 quarter course, people who are teaching a semester course, undergraduate level, graduate level, or people just doing a self-taught progress through the book.
We see that you have co-founded some startups and you have also been serving as a consultant for the industry. Um, what has been the hardest part of moving algorithms into products in your experience?
That's a really, really good question. Currently, I'm working in the blockchain world on the propagation side, the infra side. That's what
Is that
Optimum
optimum?
does. Optimum, exactly, yeah. Uh, and I have to say, I have found the Web3 community to be extremely open and interested in new ideas. I mean, hard things are always just getting the thing to work, right? We're engineers. We know we know that the thing doesn't debug itself, right? And you try something and then, it doesn't always go exactly as planned, and then you have to try again and design it back to the drawing board. I mean, we all know that, we share it, we love it, otherwise we wouldn't be in this job. But I found the Web3 community to be really, really interested, just intellectually interested in new ideas. Um, I think often the biggest problem is status quo. The status quo, are people willing to look at things from scratch? Are they curious and open-minded and want to know about how things work and look at new ideas, or are they really set in their ways? That's the biggest problem. I think it's not the technical problems.
Okay, so we had quite a long conversation. We'll
We
try
did. It was
to
great.
we'll, we'll try to close this with some quick fire at the
Sure.
end. Let us try this. So universal decoding in one sentence.
A decoder that is not completely tied to a particular code structure.
That's amazing. One underrated metric for 6G, according to you.
Latency.
Okay. One paper that you recently read, could be your own paper or could be from anyone else, that you recommend young engineers to read.
Oh, wow. Okay, there's so many. Now I'm gonna have to pick favorites.
Absolutely. That has
All
to be ready.
right, yeah, now you really
Just pick one that is at the top of your mind.
the oldies and the goodies, Elias, go back to the original Elias papers on product codes. Yeah.
All right, listeners, you know which one to read next. Professor Muriel, thank you very much for sharing your insights on 6G coding evolution, Grand, your new book on network coding, and the whole journey, your personal experience from research to startups. So, listeners, please check out Network Coding for Engineers and her papers. Uh, so, that's all for what we had for you in this conversation. I am Prakash, and thank you for tuning in. Until next time.
Thank you so
Thank you,
much,
Muriel.
Prakash. It was such a pleasure. Really, really fun conversation. Thanks a lot.